We're going to start out by talking about identity matrices and the inverse matrix. And to do that, we're going to try and make an analogy to just plain old regular real numbers. So for real numbers, the number 1 is a special number, and it's called the multiplicative identity for real numbers. What makes it so special is that any real number a that is multiplied by 1 results in a again. In effect, 1 identifies what you're multiplying by. So when I take a times 1, that's the same as 1 times a, which gives you a. Now the multiplicative identity matrix I has similar properties to the number 1. The identity matrix is a square matrix for which a times I is equal to I times a, which gives us a. So let's start out and look at some particular identity matrices and see what they have in common. A 2 by 2 identity matrix has 2 rows and 2 columns, and in the first row we have 1 and 0, and in the second row 0 and 1. So if I have a matrix capital A, which is A, B, C, D, and I take A times I, well, that means I'm taking the matrix A, B, C, D times the matrix 1, 0, 0, 1, and now I have to be careful because now I need to do my matrix multiplication. So to get the first row, first column, I multiply the first row times the first column. So A times 1, B times 0. To get the second row, first column, we take the second row times the first column. So C times 1, D times 0. To get the first row, second column, we take the first row times the second column. So A times 0 plus B times 1. And the second row, second column, I multiply the second row times the second column, which gives me C times 0 plus D times 1. When I do the arithmetic for these, what I find is I get A back again, the exact matrix I started with. So that's telling me that I is in fact the identity matrix because A times I gave me back what I started with, which was A. A 3 by 3 identity matrix is the matrix you see here below, and just like the previous one, it has ones down the diagonal and zeros elsewhere. A 4 by 4 identity matrix would be also ones down the diagonal, zeros elsewhere, but now it has 4 rows and 4 columns. Now let's make another analogy to just plain old real numbers. So for non-zero real numbers a, there is a special number called the multiplicative inverse that has a unique property. When I take a number a and multiply it times its multiplicative inverse, which is just 1 over a, I get out the identity element, 1. So for instance, a number 2 has a multiplicative inverse of 1/2, and that's because 2 times 1/2 gives me 1. Now the question arises, do matrices have a similar property? So for a matrix A, there's a special matrix called the multiplicative inverse matrix with the unique property that when I take the multiplicative inverse times A, it gives me back I, which is the identity matrix. Or the other way around, I can take A times the multiplicative inverse, and that gives me I. Now notice what we've named it here. The multiplicative inverse is called a to the minus 1. That doesn't mean that that's a negative exponent like 1 over a. That just means it's the inverse. Recall that on the previous slide we had 1/2, and that is equal to 2 to the minus 1. In that case, the negative power does exactly what it says. But here, the minus 1 just means that this property holds. So let's take a look at an example. So let's take a look at the matrix A equals, the first row is 2, 4, the second row is 1 and negative 1. For that particular matrix, the inverse of A minus 1, has in the first row 1/6 and 2/3, and in the second row 1/6 and negative 1/3. Let's go ahead and work out what A times the multiplicative inverse A minus 1 is. So I've taken my two matrices and I've written them down, and now I need to carry out the matrix multiplication. I take the first row times the first column, so 2 times 1/6 plus 4 times 1/6, and that goes in the first row, first column of the result. I take the second row times the first column, so 1 times 1/6 plus minus 1 times 1/6. I take the first row times the second column, 2 times 2/3 plus 4 times negative 1/3. And I take the second row, second column, which is 1 times 2/3 plus negative 1 times negative 1/3. And that all goes in my first matrix. If you look carefully, you'll see that 2 times 1/6 is 1/3, 4 times 1/6 is 2/3, and 1/3 plus 2/3 gives me 1. If you look at the other elements in this matrix, you'll see that they simplify and just give you the elements in the matrix I. And that's exactly what we wanted to have happen here. Now what if I switch it around? Now I put the inverse in front and I multiply that times A. Well, if I work out my rows and columns, I get the entries you see here below. So for instance, the second row, second column is 1/6 times 4 plus minus 1/3 times minus 1. And if I simplify all these values, I see again I get the matrix I as I should. So remember, A minus 1 is not the same as 1 over A. And the main reason for that is because division by A doesn't make any sense. You can't divide by a matrix. You can only multiply.